would like to add just a few details about the IPCC to the wonderful webcast that you guys already created. This is just to add some figures or maybe some extra things that I want to make sure that you remember from the different questions that I asked you. So I asked you to look at temperature, and you guys told me how the temperature had been changing through time. And spatially, I want to show you a figure of where we have the most temperature increases. And we see those in the mid-latitudes to the higher latitudes and typically over land masses. And you can see everywhere that we have oranges and reds and purples, we have an increasing temperature change, and it's highest over these land masses. This figure is just showing grid cells or squares that have actual measurements over something similar to this time period, back to 1901. So kind of like the data you guys are using for your project. Another data set that's also shown in the IPCC does something called interpolating. So it takes some data and it guesses what might be going on in those areas that don't have very much data, or maybe are missing some of the early years. That's called interpolation. This data set shows interpolated temperature, and you can see especially in the Arctic, in the northern hemisphere, the high latitudes, that we have the highest amounts of warming have occurred, we believe, in that area. I also asked you all about heat waves and how daytime and nighttime temperatures are changing. So we've seen that globally on average, the maximum daily temperature is warming. We've also seen that the nighttime, the minimum temperature is warming, and the nights are warming more than the days. So this results in a diurnal temperature range, or the difference between your daytime maximum and your nighttime minimum. We have a diurnal temperature range that is decreasing. So there's not as much of a spread in temperature, even though they are both warming. Temperatures at night are warming at a faster rate. What this does is it shifts the whole distribution of temperatures that we experience. So we have the average temperature of the day is increasing, the coldest temperatures of the days are increasing, and the hottest temperatures of the days are increasing. This results in more hot weather and also more record hot weather or heat waves. If we look at the warm night occurrences spatially, in this figure, everywhere that's cream, brown, red, or black is estimated where we have trends in warm nights. And you can see that pretty much everywhere over land has significant warming at night. And on the right, we see the anomaly in number of days for the whole globe. And what happens to the humidity when the air is warmer? Warm air can hold more water. So in this figure, we see from 1973 to 2012 the trend in humidity, and it's almost blue everywhere. So we've got warmer air and it's holding more water, so we have higher humidity. If I scoot down to the bottom, this is the global average of specific humidity, and you can see over time globally it's estimated to have been increasing. I also asked you about extreme precipitation events, and I just wanted to show you spatially. This is the trend in daily precipitation intensity, and where we have blue colors we have an increase in precip intensity. So it's not necessarily raining more often, but when it does, it's more intense. And you can see that over most of the United States, we have an increase in precipitation intensity. Pretty much everything east of, well, and including some of the Rockies, but everything east of the Rockies, the Pacific Northwest, the Southwest is all increasing in intensity. Same thing with Eurasia, and we have just a few areas where it's actually decreasing in intensity. Aside from intensity, just in general, where are we getting more precipitation and where are we getting less precipitation? On the left, you can see the trend from 1901 to 2010, so more than 100 years of data. we see that in the United States, for most of the U.S., with the exception of the Southwest, we had increasing precipitation amounts. The figure on the right, this is just showing the last 60 years, 1951 to 2010. So remember, same thing with temperature. The temperatures are increasing, and they're increasing more rapidly as we progress toward the present time. So precipitation is increasing, and in some areas it's increasing more rapidly in the last 50 years. In some areas, and this is maybe even worse, it's decreasing more rapidly. And in particular, in Africa, in the Sahel region, there are severe droughts, decreasing precipitation amounts. And unfortunately, this is an area where people don't have the means to necessarily adapt to this situation. Now, I noticed that nobody during class asked me about this figure that I put in your packets. This is a picture of a flying buttress. A flying buttress is an architectural element that helps support really large buildings. Here's a picture of flying buttresses supporting the side of this cathedral. And the reason why I put this picture in there, and why it's on the slide where I mention ice sheets, is because the sea ice that we have around the Antarctic continent. So there's ice on the Antarctic continent in the South Pole, and then there's sea ice that extends out from that ice sheet. That sea ice acts like a flying buttress to keep the ice sheet on the continent. Now we're seeing rapid decreases in sea ice, and this figure are satellite estimates that are showing where we have accumulation of snow, so that we would have an increase in elevation because we're building the ice, and where we have an accumulation, it's yellow, orange, and red. So you can see the center of Greenland, we're actually accumulating ice. And in the southern hemisphere, you can see that there are parts of the Antarctic ice sheet where we are accumulating ice. But in the blues and purples is where we are losing ice. And in Greenland, that's along the edge of Greenland. And that's where we have outlet glaciers that go into the ocean. They're melting more rapidly. And so we're losing ice on the edges of Greenland. In the southern hemisphere, in the Antarctic, we're rapidly losing the sea ice, or losing our flying buttresses. And when that happens, we start to have decreases in the ice mass along the edge because we don't have those flying buttresses keeping the ice up on the continent. And that's what you can see here, that in some areas around the edge of the Antarctic ice sheet, we have melting. And this is not only a problem for sea level rise, but also all of the animals that rely on the sea ice to live and hunt. I also asked you guys about RCPs, and you did a great job of defining them and talking about the temperature projections, but let me just clarify what exactly they are. They're different descriptions of the possible climate futures, and this all depends on how we control emissions in the future. They are named after the possible range of the radiative forcing values in the year 2100 relative to pre-industrial values. So in green here we have RCP 2.6. This would mean that our radiative forcing values would be 2.6 watts per meter squared greater than pre-industrial values. In purple we have RCP 4.5. This means our radiative forcing is 4.5 watts per meter squared greater than pre-industrial values. In orange we have RCP 6.0. This is 6.0 watts per meter squared more radiative forcing than pre-industrial values. And then the big one, RCP 8.5, is 8.5 watts per meter squared more radiative forcing than pre-industrial values. Why did I ask you to define committed change? Well, if all of our anthropogenic forcing mechanisms were held to the same levels that they were in the year 2000, we would still warm, because we still have those chemicals in the atmosphere. We still have the greenhouse gases in the atmosphere. And we see that we would warm about 0.1 degrees Celsius per decade for the next 2 decades. So that's what we've already done. That's already going to happen. And so these are consequences that we have to deal with. It's going to happen. We have to deal with it. We have to adapt to what we've done. This figure is showing the different, basically RCPs that were used in Working Group 1 for the 4th assessment a few years ago. And they just name them differently. But in orange, and I've pointed an arrow to it, you can see what our year 2000 concentrations would produce. So even if we stopped emitting at any higher than the year 2000 rates, we still would incur that warming. That is our committed change. We've already committed to that warming. I also asked you to define equilibrium climate sensitivity. And you guys defined it in your webcast, but I got a feeling that you didn't really get it or get why I asked you to define it. So way back at the beginning of the semester, I talked about the ways that climatologists would use computer models to look at the atmosphere and look at the Earth's system. And one of the ways was that we would slowly turn up CO2 and watch what happened. The other way was I called it smack the model. We would dump a bunch of CO2 in it and wait for it to get to equilibrium and see what the temperatures were like. Well, compared to the Earth's history, humans have practically, in the blink of an eye, doubled CO2. We just dumped a ton of CO2 into the atmosphere, and now the Earth's system is coming to equilibrium. So in the report, they would talk about having people run models with this doubling of CO2, and they estimate that when the Earth finally comes to equilibrium, gets used to that doubling of CO2, temperature will rise between 1.5 degrees and 4.5 degrees Celsius. So basically, for what we've done, that's the temperature rise we can expect, somewhere between 1.5 and 4.5. I hope that this webcast just helps add to the work that you guys have already done and maybe helps clarify a few things.